Welcome to Rhythm Genesis, a rhythm game that puts creative power in your hands. Unlike traditional rhythm games locked to premade songs, Rhythm Genesis lets you upload your own music, automatically generate beat maps using our signal processing algorithm, fine-tune them using our in-game editor, and play them interactively. On the left, you can see the architectural diagram of our game, which is organized into four major subsystems. First, we have the user interface subsystem. This includes the main menu, the actual gameplay animations, the scoring system, the bitmap editor for fine-tuning rhythm charts, and the upload window where users can upload music from their local machines. Second is the game logic subsystem. This handles the core mechanics of the game, such as managing game states, spawning nodes, calculating scores, and processing player inputs. Third is the audio and bitmap processing subsystem. It includes our audio processor, which is implemented using Python's librosa library. It also includes the in-game bitmap editor and the C++ Python bridge that connects the audio processing backend with our game engine, which is entirely written in C++. Finally, we have the data storage and management subsystem. This subsystem stores bitmaps, which are essentially JSON files, either auto-generated by our Python scripts or manually created using the editor. It also manages the music files used as background tracks during gameplay, as well as user-specific game settings. We originally chose Unity to implement our game because it's a powerful and popular game engine. But for our 2D rhythm game, it quickly became clear that Unity was overkill. So we decided to implement our own game engine using C++. It is lightweight, fast, and gave us full control. As you can see in the C makelist file, our game uses several essential libraries. SFML, or Simple and Fast Multimedia Library, handles graphics, audio, and input, which is perfect for our 2D game. spdlog helps us log debug info efficiently during development. Python 3 is integrated to run our bitmap processing code using librosa. Tiny file dialogs give us simple file picker windows for music uploads. And finally, Lowman.json makes it easy to load and save bitmaps in JSON format. This is the user interface system I built from scratch for our game engine using C++ and SFML. On the left is the folder where all the UI code lives. What I have done is build a flexible system where every visual element on screen, like buttons, labels, and sliders, can be created from reusable building blocks. It all starts with something called a UI element, and you can see its C++ header file. Think of this like a Lego base brick. Every other UI piece is built on top of it. This base class knows where the element is on screen, how big it is, and whether it should be shown or hidden. It also defines two core abilities, how the element draws itself and how it reacts when you interact with it. For example, the UI button element creates a rectangular shape that shows text. If you click it, it can run any action you assign, like starting the game or loading a file. This works thanks to an event system that listens for things like mouse movement or button clicks. Once I had these core components working, I used them to build bigger, more complex interfaces. For example, the main menu combines a bunch of buttons and a scrollable list. Now let me explain other subsystems to you. The bitmap editor is where users create and fine-tune rhythm game charts, or bitmaps. It contains custom buttons, text input boxes, and a scrolling waveform viewer that syncs perfectly with the music during playback. To make uploading songs easy, we integrated the Tiny File Dialogs library. So when users choose a music file, a simple file explorer window pops up. There is also the storage system that stores JSON bitmaps that are either auto-generated or manually created, as well as the music files in the game's assets folder. And finally, because our audio processing system is implemented in Python, I implemented this C++ and Python bridge so that we can directly call Python functions in our C++ game engine.
The audio analysis subsystem of the project detects the rhythm of the uploaded songs in order to determine when the tiles in the game should fall. We implemented the rhythm detection using a library called librosa. First, we compute the spectral flux onset strength envelope, as you can see in the bottom figure on the right. Then we select the timestamps with the highest onset strengths, as those will correspond with the start of notes. One consideration in trying to calculate the threshold above which a timestamp should be considered a note is that we much prefer false negatives to false positives, as having a tile not fall on a note in the song will simply make the game easier, but having extra tiles that do not correspond with the rhythm would be confusing and frustrating for the player. We explored a few different methods of determining this threshold. The first method we tried was simply a fixed top percent. This was prone to false positives at slow tempos and false negatives at fast tempos. Another method we tried was using a formula based on the mean and standard deviation. This method yielded high accuracy across all tempos. We also explored using the median and median absolute deviation, as this formula would be less affected by outliers, but this produced more false positives. The final version we tried used a sliding window to compute the threshold locally instead of globally. This, however, was more susceptible to noise. So we ultimately decided to use the formula involving the mean and standard deviation, as this was highly accurate with the least false positives. Another use case requirement was that the duration of processing a song should be less than 10 seconds, as this is the amount of time users on average will wait for a process before switching contexts. Our latency tests verified that a 5-minute song would on average take about 4 seconds to process. Here's a unit test that we ran on all 4 methods. On the right is a simple piece I composed in MuseScore, which we ran the rhythm detection on. The figure on the left shows the accuracy of each method at tempos ranging from 50 to 220 beats per minute. Here's the performance on a composition that serves as a stress test, as it has much more complex rhythm and also includes dynamics, different articulations, and varying tempo within the piece. We also tested on many real songs as well. For these, we manually verified the accuracy of the rhythm detection by ear through playing the audio while animating a circle to flash on the detected beats. This subsystem works best on songs with single instruments such as piano, guitar, and violin, as they have more distinct note onsets. For voice or multi-instrumental songs, the user may prefer to create their own beat map using the in-game editor. The output of the audio analysis subsystem is a JSON file that contains the timestamps of the detected notes, whether it should be a single note or a chord, its onset strength, and which lanes the tile should fall from. This is how the subsystem integrates with the core game loop, which reads this JSON file.
So the game itself is pretty rudimentary. I'm going to be demoing with 2 quick songs, one of them created by our actual algorithm and the other just a quick example of a shorter song so that we can see the scoring system and whatnot. So this first song is Clair de Lune. It was created by our beat detection algorithm. As you can see, the notes fall in unison with the song. I'll let this play for a little bit. And then the user can obviously click the corresponding key to hit the note at the correct time. So it's a quick example of that. And then as you can see, the game gives you some feedback with the color of the note based on how close you got it to the correct timing. And then it also updates your score on the top left. And then at any time, the user can pause the game and return to menu to select a new song to play. Then from here, we'll go to the other song, which is actually the audio and the game itself are not synced up for this one. It's just a shorter song that I mostly use for testing. And I'm going to show as a quick example here. So same thing really, playing the game, and then when it ends, the music stops, it'll display your score. And then these bars at the top show the actual notes that you hit in order. So my first note was perfect. The second note that I hit was bad, etc., etc. And then down here is sort of a scoring breakdown to show what percentage of your points you had accumulated at what time in the game. That's the scoring system, and then from here you can return to menu and start a new song.